This video is about stabilization theory. It's really intended only as an overview of stabilization theory, and subsequent videos will provide detailed documentation and examples of the various points that are made in this overview. Now, stabilization theory assumes that the typical form of life arises abruptly, then persist unchanged or virtually unchanged up to the time of its extinction. Whereas conventional evolutionary theory, neo-Darwinian theory, thinks in terms of populations, that is, um, the population of individuals making up a particular form of life changes gradually over time as individuals absorb mutations and accumulate them, and all this occurs under the influence of natural selection as the individuals that have favorable traits survive and leave offspring, and those that have less favorable traits do not survive and do not leave offspring, or at least do so at lower rates, so that the favored type comes to the fore. Now, either of these ways of thinking about evolution, just conceptually, you can imagine them occurring, but which of them is more consistent with data? That is, which of them is more consistent with observation? Now, I have to say that stabilization theory is more consistent. That is, the typical fossil organism, the typical fossil form, when you look at the fossil record, appears abruptly and then persists over time, sometimes for millions of years, typically, I would say about 10 million years, and then it goes extinct. And during that period of time, it doesn't change significantly. You can look at the latest specimens in the record, and they look very similar to the earliest specimens. And actually, I talked with Stephen Jay Gould once about this at a conference, and he said that this is just an obvious fact that's accepted by paleontologists. And I said that I didn't think that geneticists would accept it because it sounds magical. It sounds as if it's something that couldn't happen. In other words, what genetic changes would cause a new type of organism to suddenly appear, and then what types of processes would maintain that organism unchanged for millions of years. And he said, well, it doesn't make any difference if geneticists can't think of a reason why it might occur or how it might occur. What's important is that it's been observed, it's an empirical fact, and that they have to accept it. So at that point, I decided to start thinking in terms of what sort of genetic processes could account for that observed fact, that observed punctuation and stasis, as Gould terms it. In other words, the punctuation is the sudden appearance of a new form, and the stasis is the subsequent lack of change in that form up to the time of its extinction. So then, what sorts of genetic processes could possibly produce this observed pattern of punctuated equilibrium, of abrupt appearance and subsequent long-term stability that's seen in fossil life forms? Well, there are actually several such processes that are known and well documented. And I call them stabilization processes because they produce stable new forms of life. So, what then is a stabilization process? Well, as we all know, each different type of organism, each life form, is composed of individuals which are capable of reproducing themselves in every generation, so that one generation gives rise to another generation of individuals of a similar type. In some cases, life forms are able to reproduce themselves very accurately for amazingly long periods of time. For example, the horseshoe crab has been able to reproduce itself for 300 million years and more with little or no change, so that a horseshoe crab today looks much like a horseshoe crab did long ago in the Paleozoic, 300 million years ago. And yet there are certain events which can disrupt this amazingly accurate cycle of replications, so that parents can, even in a single generation, give rise to offspring that are unlike themselves. One such event is a hybrid cross. For example, horses have gone on producing horses generation after generation for thousands upon thousands of generations. And donkeys have produced donkeys for also thousands of generations. But then a horse can mate with a donkey, and then suddenly the offspring is neither a horse nor a donkey. It's a mule. It's something new. It's something that is unlike its parents. Of course, many people would say that you can't get a new form of life that way because a hybrid wouldn't be able to propagate itself. But this way of thinking is erroneous in two different ways. The first is that while mules are quite sterile, there are many other kinds of hybrids that are not. And there are tens of thousands of different types of hybrid crosses known. And I would say most of those crosses, just looking at the data, in most of those crosses, the hybrids can produce offspring. So the mule is not a good representative of hybrids in general. Moreover, there are many life forms that can propagate themselves without sex, and sterility is only a problem when you're talking about sexual reproduction. If you're talking about vegetative reproduction or various other methods of reproduction that do not involve sex, then sterility is no problem whatsoever. So obviously, if you had a hybrid cross produce an organism that was capable of reproduction without sex, then immediately you would have a new, stable life form that could go on reproducing itself indefinitely. For example, it's been proved that various American lizards of the genus Nematophorus came into being in exactly that way. A hybrid cross produced offspring that were capable of asexual reproduction, and they propagated themselves in that way. The resulting population of lizards, which is now treated as a species, Nematophorus neomexicanus, came into being millions of years ago and has been reproducing itself without sex ever since. Note that this particular type of stabilization process, that is, a hybrid cross producing an asexual life form, is consistent with what's been observed in the fossil record. That is, the new type of organism would appear abruptly, very suddenly, and then subsequently it would persist unchanged up to the time of its extinction. This is because asexual reproduction is clonal. It gives rise to no variation. The parent is exactly like the offspring. So it just goes on cycling indefinitely, potentially for millions of years, with no variation occurring. So already, even though we've only covered one of the various different types of stabilization processes, we've been able to come up with an explanation of the origin of perhaps half the organisms on Earth, because about half of all animals, plants, and fungi on the planet are capable of reproducing asexually. Moreover, it's reasonable to suppose that Asexual life forms typically arise in this way during the course of evolution because, in the case of every asexual life form where the origin of that life form has been scientifically determined, it did have such an origin. We've seen how stabilization theory accounts for the origin of asexual life forms. Well, what about the other half? What about life forms that do use sex to reproduce themselves? Where do they come from? How does stabilization theory explain them? Well, if you recall, I've already talked about the fact that many hybrid crosses, produce hybrids that are not sterile. So stabilization theory incorporates these observations. That is, it assumes that various sexual life forms arise as various sexual hybrids recover their fertility and get established as new forms of life. Now, at the genetic level, there are various ways that this can happen, and each of these ways can be described as a different kind of stabilization process. But I'm not going to get into all the details of that here in this overview. For the present, suffice it to say that each of these different stabilization processes produces a new sexual life form in a very rapid fashion, that is, in a single generation or at most a few generations, and that the resulting form is stable thereafter, which is, of course, consistent with what has been observed in the fossil record.